When we talk about training methods in large language models, one of the most important stages is pretraining. Pretraining is the process by which a model learns general language patterns before it is fine-tuned for specific tasks. It is the foundation that gives the model its broad capabilities. Without pretraining, a model would have to learn everything from scratch for each task, which would be inefficient and limited. With pretraining, the model acquires a wide base of knowledge and linguistic competence that can be adapted to many different applications. Pretraining involves exposing the model to massive amounts of text data. This data can include books, articles, websites, code, and other sources. The goal is not to memorize the data but to learn the statistical structure of language. The model learns how words and phrases relate to each other, how sentences are formed, how meaning is conveyed, and how context shifts across discourse. By processing billions of tokens, the model builds internal representations that capture syntax, semantics, and even elements of world knowledge. These representations are stored in the parameters of the network, which can number in the billions. The core objective of pretraining is usually language modeling. In its simplest form, this means predicting the next word in a sequence given the previous words. For example, if the input is the cat sat on the model learns to predict Matt as the most likely continuation. This task may seem trivial, but it forces the model to learn deep patterns of language. To predict the next word accurately, the model must understand grammar, semantics, and context. Over time, the model becomes highly proficient at anticipating language, which translates into the ability to generate coherent text. There are variations on the language modeling objective. One common approach is masked language modeling, where certain words in a sentence are replaced with a masked token, and the model must predict the missing words. For example, the cat sat on the mask requires the model to infer Matt. This approach encourages the model to use both left and right context, making it bidirectional. Another approach is causal language modeling, where the model predicts each word based only on the preceding words. This is the method used in autoregressive models like GPT. Each approach has strengths, and some models combine them to balance bidirectional understanding with generative ability. Pretraining is computationally intensive. Training a large language model requires enormous datasets, powerful hardware, and sophisticated optimization techniques. The model processes text in batches, computes predictions, compares them to actual tokens, and adjusts its parameters using gradient descent. This process repeats billions of times, gradually shaping the model's internal weights. The scale of computation is staggering, involving clusters of GPUs or TPUs running for weeks or months. The result is a model that has absorbed patterns from vast amounts of text, giving it broad linguistic competence. One of the remarkable outcomes of pretraining is emergent behavior. As models grow larger and are trained on more data, they begin to exhibit capabilities that were not explicitly programmed. For example, they can perform arithmetic, translate languages, or answer factual questions, even though they were never directly trained for these tasks. These abilities emerge because the model has internalized general patterns of reasoning and knowledge during pretraining. This phenomenon has led researchers to explore scaling laws, which describe how model performance improves predictably with more parameters, more data, and more computation. Pretraining also raises questions about data quality. The model learns from whatever text it is exposed to, which means that biases, errors, and misinformation in the data can be reflected in the model's behavior. If the training data overrepresents certain viewpoints or underrepresents others, the embeddings and attention patterns learned during pretraining may carry those imbalances forward. Addressing this requires careful curation of datasets, filtering of harmful content, and techniques for debiasing. Nevertheless, the sheer scale of pretraining makes perfect control difficult, and ongoing research seeks to mitigate these issues. Another important aspect of pretraining is tokenization. Before text can be fed into the model, it must be broken down into units called tokens. These tokens may be words, subwords, or characters, depending on the tokenizer. Each token is mapped to an embedding, which serves as the input to the transformer. The choice of tokenizer affects how the model learns during pretraining. Subword tokenization, for example, allows the model to handle rare words and morphological variations more effectively. It ensures that even unfamiliar words can be represented as combinations of known subwords, making the model more robust. During pre-training, the model does not just learn about language in isolation. It also absorbs world knowledge encoded in text. If the training data includes encyclopedias, scientific papers, or news articles, the model learns facts about history, geography, science, and culture. This knowledge is not stored as explicit entries but as distributed patterns in the parameters. As a result, the model can answer questions or generate explanations that draw on this implicit knowledge. However, because the knowledge is statistical rather than symbolic, it can sometimes be inaccurate or outdated. This is why retrieval-augmented methods are being explored, where pre-trained models are combined with external databases to improve factual accuracy. Optimization during pre-training involves techniques like ATOM or ATOMO, which adjust learning rates adaptively. Regularization methods such as dropout prevent overfitting. Gradient clipping ensures stability. Learning rate schedules, such as warm-up and decay, help the model converge effectively. These techniques are crucial because training at such scale is prone to instability. Without careful optimization, the model could diverge or fail to learn meaningful patterns. The engineering of pre-training is as important as the conceptual design, requiring meticulous tuning of hyperparameters and monitoring of training dynamics. Pre-training also interacts with architecture choices. The size of embeddings, the number of attention heads, the depth of layers, and the width of feed-forward networks all affect how well the model learns during pre-training. Larger models generally perform better, but they require more data and computation. Smaller models can be trained more efficiently but may lack the capacity to capture complex patterns. Researchers explore trade-offs between size, efficiency, and performance, seeking architectures that maximize the benefits of pre-training within practical constraints. The impact of pre-training extends to downstream tasks. Once a model is pre-trained, it can be fine-tuned on specific datasets for tasks like sentiment analysis, question answering, or summarization. Fine-tuning adjusts the pre-trained parameters slightly, aligning them with the requirements of the task. Because the model already has broad linguistic competence, fine-tuning requires less data and computation than training from scratch. This transfer learning paradigm has revolutionized natural language processing, making it possible to build powerful models for specialized tasks with relatively modest resources. Pre-training also supports zero-shot and few-shot learning. In zero-shot learning, the model performs a task without any fine-tuning, relying solely on its pre-trained knowledge. For example, it can translate a sentence even if it was never explicitly trained on translation. In few-shot learning, the model adapts to a task with only a handful of examples. These capabilities arise because pre-training has given the model a flexible, general understanding of language. It can apply this understanding to new tasks with minimal guidance, which is a major step toward general artificial intelligence. The scale of pre-training has led to discussions about sustainability. Training large models consumes vast amounts of energy and resources. This raises concerns about environmental impact and accessibility. Researchers are exploring ways to make pre-training more efficient, such as using smaller models with clever training strategies, distilling large models into compact versions, or reusing pre-trained components across tasks. The goal is to balance the benefits of pre-training with a need for responsible resource use. Ethical considerations are central to pre-training. Because the model learns from large datasets, it can inadvertently absorb harmful stereotypes, offensive language, or misinformation. These issues can manifest in outputs, raising concerns about fairness, safety, and trustworthiness. Addressing them requires not only technical solutions but also governance and oversight. Transparency about training data, accountability for outputs, and mechanisms for correction are all part of the ethical landscape of pre-training. Looking forward, pre-training will continue to evolve. Researchers are experimenting with multimodal pre-training, where models learn from text, images, audio, and video simultaneously. This creates embeddings that align across modalities, enabling richer understanding and generation. Others are exploring continual pre-training, where models are updated incrementally with new data rather than retrained from scratch. This would make models more adaptive and current. There is also interest in combining pretraining with symbolic reasoning, grounding statistical patterns in logical structures. These directions suggest that pretraining is not a static method but a dynamic field of innovation. In summary, pretraining is the stage where large language models acquire their broad competence. It involves massive datasets, complex optimization, and enormous computation. It produces embeddings and attention patterns that capture the structure of language and knowledge. It enables transfer learning, zero-shot learning, and emergent behavior. It raises challenges of bias, sustainability, and ethics. And it continues to evolve toward multimodality, continual learning, and hybrid reasoning. Pretraining is the foundation of modern AI, the process that turns raw text into intelligence, and the reason large language models can perform such a wide range of tasks. Without pretraining, these models would be narrow and brittle. With pretraining, they are versatile, powerful, and transformative.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.